Hey guys, before we start talking about what kinematics is, let's take a few seconds, pause the video, and do this warm-up right here. Hey, welcome back. You can unpause the video. So I wanted to save some time, so I did it off to the side. And let's talk about what we got. So for the first part, when we're talking about the average velocity, we're talking about the average rate of change between 2 points. That's basically the slope of the secant line that connects the 2 points, right? And then we found earlier in the year that when we shrink the distance between those 2 points, we arrive at the instantaneous velocity at a specific time. So I just wanted to show you kind of this on a graph is when we found the average velocity between 1 and 5 of the particular function given in letter A. And then this is, okay, so like when I use the geometry feature on here, it doesn't always make it perfect. So we should have gotten 10 as the slope of the secant line, the slope of the tangent line, but it has 9.99. Let's just call that fancy 10. But that is the slope of the tangent line when time equals 5, okay? That is the instantaneous velocity when time equals 5. So we were just kind of going over, the difference between the two and an application to kinematics. So what is kinematics? Kinematics is a branch of physics, hey, throwback, and math, concerned with the motion of a body along a straight line without consideration of the forces involved, right? So we have a straight line, we have the origin, and then we talk about a body's movement along that line, and we describe its position, its velocity, its acceleration, its displacement, its total distance traveled. Those are basically the things that we're going to talk about in kinematics. Okay, so let's talk about how we would describe each piece of motion along a line. Let's look at the position function, okay? So the position function is going to tell us the body's position in relation to the origin, right? So I think the best illustration of this is with an applet called the moving man. So here, I have to undo my thing here, so just give me a second. Okay, so when I talk about this guy's position, right, the origin is 0. Let's say we changed this to -10. No, that's too far. -5. Look what happens. He is to the left of the origin. Now let's see when his position in relation to the origin is positive. Where does he go? He goes to the right of the origin, okay? So the position is going to tell us whether we are located to the right of the origin, when it's positive, at the origin, when it's 0, or to the left of the origin when it's negative, okay? So that is the position function. That is referred to as the original, right? Whenever we're saying, oh, f of x is the original. The position function, s of t, is the starting original function, right? Then we can talk about the velocity, okay? So we're skipping displacement and speed for a second. We're going right to velocity. So velocity is something that's known as a vector quantity, which means that it has a magnitude and a direction, right? So velocity is like you are heading to the right 12 units per second. You are heading to the left 12 units per second. So let's look at what velocity, or the rate of change or gradient of the position, looks like on the moving man applet. So as I manipulate the velocity, right? Let's have him start at 0. Okay, so velocity, when it's positive, right? So it has a direction, it's a vector. It's going to be heading in the, oh no, this is like over my spot here. Go, no. Here, let's see if I can move this. Sorry. Let's move this. I figured it out. Okay, great. Marginally. Here, let's get that up there. Perfect. Okay, so let's have him move to the right 5 meters per second. Perfect. So let's have him start at the origin again. And now let's have him move -5 meters per second. He's still moving at the same speed. He's just moving in the opposite direction, okay? He's heading to the left. So that's what we mean by velocity is a vector quantity with both a magnitude, aka displacement per units, right? And a direction, right or left, indicated by its sign, okay? Now let's talk about acceleration. This is whether the body, in this case the moving man, is speeding up or slowing down. So this is the rate of change of the gradient of velocity. So how much is his speed or velocity going up or going down, okay? So let's have his velocity be 1, and let's have him start all the way to the left because I want you to really see what happens. So now his acceleration is +1. So that means he is speeding up at an increasing rate. Check it out. He starts going kind of slow, and then he's like, whoa, 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 whoa. Okay. Let's have him do the same thing. Now he's going to start at 10. His velocity is going to be negative, meaning he's moving to the left 1 meter per second. But now he is speeding up in the left direction quite quickly. Check it out. Look, he's going, whoa, 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 whoa. Okay, so I want you to kind of think about this really quickly. He's going to start here, and now I'm going to have him heading to the right at 1 meter per second, but now I'm going to have his acceleration be heading in the opposite direction. Actually, let's have this be a little faster here. Okay, what happens here? Look at that. He is slowing down until he has to change directions, right? Okay, so when the velocity and the acceleration, now he's changed direction, so you don't really know what I'm talking about, but when the velocity and the acceleration have an opposite sign, the body is slowing down. Now let's talk about that, but we're gonna have him go in the opposite direction. So now we have opposite signs, right? This guy's gonna go in the negative direction, but let's have him go a little faster. The signs are opposite. So what's happening? Slowing down, slowing down, slowing down, slowing down, slowing down until he turns around, okay? So when the velocity and acceleration have opposite signs, the body is slowing down. When they have the same sign, the body is speeding up. Okay, that is summarized right here in this little spot. Okay, think about how we would determine what the sign of the velocity and the sign of the acceleration are. We would make number lines, right? So let's talk about their cool relationship back in our notes. So remember, the rate of change is just a fancy word for the derivative, slope, or gradient. Okay. So if we know that the velocity is a measure of the rate of change of position, in order to get the velocity function, what I can do is take the derivative of the position function. Then, if I know that acceleration is the measurement of the rate of change or the gradient of the velocity, I can take the derivative of the velocity function to get the acceleration function, okay? So this is their relationship and how it applies to derivatives, okay? So think about it, right? If I'm trying to figure out some information about a moving body, right, I've got its velocity number line, I've got its acceleration number line, okay, and then I'm determining kind of the signs along the line just the same way that I did with first and second derivatives, okay? He is akin to the first derivative and he is akin to the second derivative, okay? So this page kind of goes over, once we have our two number lines of velocity and acceleration, how we would interpret their signs, okay? And this is more for your reference than for me to like sit here and go over with you. So why don't you pause the video, take a few seconds, take it all in, and read up to example 1, okay? And then all right, so I think you'll probably notice at this point that there's a couple of terms that we've kind of glazed over, and they are displacement, speed, and total distance traveled, okay? The reason why we're kind of glazing over those is because I would rather discuss them in person with example number 4. I have a easier way to understand them than kind of in the context of this situation. So let's go through these problems here, and then just know that we will learn about displacement and speed when we come back to class and we talk about it, okay? So let's do example number 1 together. It says, a particle moves in a straight line with a position relative to 0 given by s of t equals t cubed minus 3t plus 1, where t is time in seconds and t is greater than 0. Example A says, find expressions for the particle's velocity and acceleration and draw sign diagrams for each of them. Okay, so if I'm trying to find an expression for the particle's velocity, I'm going to take the derivative of the position function, which is s of t. So v of t is going to be equal to 3t squared minus 3. The acceleration function is going to be the derivative of the velocity. So we have 6t is my acceleration function, okay? So if I need to find expressions for them, I did that. And then now I just have to draw sign diagrams for each of them. Sign diagrams are also number lines, if you want to think about them like that. So let's figure out how we would draw a number line for the first derivative, aka v of t. I would set v of t equal to 0, and I would get my critical points as -1 and 1. But it says that t is greater than or equal to 0, so I'm only going to have one critical point. We start when t is equal to 0, and then we go up and we have one critical point at 1, okay? And that is a 0. So let's test the sign to the left of 1. So in between, maybe let's do 0.5. So that would end up being, I'm testing the first derivative with 0.5. So I would have 0.5 plus 1, that's going to give me a positive. 0.5 minus 1 is going to give me a negative, so I would have positive times a negative, and that's going to give me a negative. Then to the right of 1, I would have maybe, let's try 2. So I would have a positive, positive, positive. This would all be positive. So I have my sign diagram for V. And then let's find our sign diagram for A. So let's set the second derivative, or the acceleration function, equal to 0. Time is equal to 0. So remember, we said that time only starts at 0, so we kind of just have no interval to test. This is like the example that we did in class where we had the e function, and it was like, prove that the original is always increasing, right? So we just have our second derivative, and we just have to test some random value on here and prove the sign of the acceleration is either positive or negative. Let's find out. So let's pick 1. Let's plug 1 into the second derivative. That's a positive number. Okay. So that is our sign diagram number lines. Yeah, we did it. Okay. B, find the initial condition. So initial conditions are when time is equal to 0, and hence describe the motion at this instant. Okay, so if I have to describe the motion, I'm going to need to mention the position, the velocity, and the acceleration when time is equal to 0. Okay, cool. So let's evaluate s of 0 and figure out this, particle's starting spot. So I've got 0 cubed minus 3 times 0 plus 1. S of 0 equals 1. So remember the moving man, when the position is positive, we are to the right of the origin. So that means the particle starts 1 unit to the right of the origin. Okay, and thus the velocity would be 0 minus 3. Okay, so, sorry, this is v. Let's see. V of 0 is equal to 3 times 0 squared minus 3. And we have a negative initial velocity, meaning the particle is heading to the left initially, which is confirmed by our sign chart up here, right? We saw that it's initially heading left. And the acceleration is always positive. So the acceleration at 0 would be 0, so it didn't start doing anything yet. So we would just say the particle starts 1 unit to the right of the origin and it's heading to the left. All right, cool. Let's C. Now I have C. Describe the motion of the particle at t equals 2 seconds. So it's the same thing, right? We have to evaluate S, V, and A for 2, and then comment on what's happening, okay? So I would have S of 2 is equal to 2 cubed minus 3 times 2 plus 1. That's going to give me S of 2 is 3. And then I have V of 2. That's going to be 3 times 2 squared minus 3. That's going to give me 9. And then I have A of 2 is equal to 6 times 2, which is 12. Okay, so S of 2 equals 3. V of 2 equals 9. And A of 2 equals 12. So this is going to be meters per second, and this is going to be meters per second squared. So what would we say here? Both of these are positive when t equals 2. So that means since acceleration and velocity have the same sign, the particle is speeding up. So we would say both acceleration and velocity are positive. Remember the moving man. So the particle is speeding up to the right. And, oops, it is 3 units to the right of the origin when t equals 2. Okay, part D. Find the position of the particle. So we're evaluating S of when the particle changes, of the particle when changes in direction occur. So changes in direction occur when the velocity is equal to 0. So we got to find what t that happens at and then plug it into the position function, okay? So we already found the time when the changes in direction occur, and that happened at 1, when time equals 1, right? Look at our velocity number line right here, okay? We had a change in direction at 1, so I can go ahead and evaluate the position function for S of 1. So 1 minus 3, negative 2 plus 1, negative 1. Okay, so when time is equal to 1, the particle is located 1 unit to the left of the origin. Okay, this might be kind of hard to envision, so I did want to graph it so I can show you exactly what's happening in terms of graphs. So this is a graph of the original position function, and then I cut off its domain because it said that it was only starting when time is greater than or equal to 0. So I want this thing to count by ones, so that way, yeah, or whatever, it's fine. So I see first, this is what's happening, right? So when time was equal to 0, we found that the particle was 1 unit to the right of the origin, right? It said for us to figure out the initial conditions. So we had S of 0 is equal to 1. So on the graph, F of 0 equals 1. The particle starts 1 unit to the right of the origin, right? And it says that the velocity when time is equal to 0 is negative 3, which means the particle is heading to the left, right? So it is going down. That makes perfect sense, right? It's heading to the left. It's getting more and more negative until it gets to 1, at which case, this is the minimum of the position function, right? The particle changes direction, okay? So if we wanted to think about this in terms of the original, the first derivative, and the second derivative, check what happens here. So again, I'm going to change this so that way it just starts when time is equal to 0, and then I'm going to kind of spread this out. Okay, so the blue is the original function, right? And we just examined that. So look what happens when we have our minimum. It's happening when time is equal to 1. Therefore, I'm expecting to see a change in direction, or when v of t is equal to 0 at 1. That's exactly what happens, right? And we saw that the sign, to tie this to graphs, which we just learned, the sign of the velocity function is going to be negative until we get to 1, and then it becomes positive. That's exactly what our number line shows us. Then the acceleration curve is always positive. It starts at 0 and is just positive for life. So that's kind of a tie into the graph of what's happening. A little faster now. Let's go to example number 2. It says, suppose the position equation for a moving object is given by s of t is equal to 3t squared plus 2t plus 5, where s is measured in meters and t is measured in seconds. Find the velocity of the object when time is equal to 2. So we're trying to find the velocity of the object, so we're going to need v of t, and then we're going to plug in, a 2 for t. Okay, so we are starting with the original. In order to generate the velocity curve, we are going to have to take the derivative of this thing. That comes from the first derivative of the position function. And then now I'm going to have to evaluate this when time is equal to 2. So find the velocity of the object when time is equal to 2, and then are we talking about seconds, meters per second? Okay, so we have a velocity of 14 meters per second when time is equal to 2. Example 3. A particle moves in a straight line according to the law of motion. S of t is equal to t cubed minus 4t squared minus 3t. Find the average velocity on the interval where time goes from 0 to 1. Okay, so we know that average velocity is basically just the average rate of change. The average rate of change is going to come from the change in y's. Sorry, that's a 0, and it looks like a strange item. Over the change in x. Okay, so now I'm going to have s of 1 minus s of 0. Well, what is s of 1? S of 1 is going to be 1 cubed minus 4 times 1 minus 3 times 1. So this would be 1 minus 4 is going to give me negative 3 minus 3 more is going to give me negative 6. Okay, so I would have negative 6 minus s of 0. Let's find s of 0. And this is just going to be 0, obviously. And then over 1, this would be negative 6 over 1. So we have our average velocity is equal to negative 6 meters per second over the interval from 0 to 1. Okay. So that means if we kind of sketched this and we found the slope of the secant line between 0 and 1, it would be negative 6. Got it. Now we have to find the velocity. When the velocity of the particle is 0, what is the acceleration? So we need the velocity function. We need to figure out when that is equal to 0, and then we have to evaluate the acceleration at that magic number. So let's go ahead and find the velocity curve first, and that's going to be found by taking the first derivative of the position function. So I'd get 3t squared minus 8t minus 3. Okay, and I'm going to set that equal to 0. That means I'm finding the when, or the time, when we are equal to 0. All right, and then I would just factor this. Okay. I'm going to reject this because time cannot be 0. Let's just write negative. Okay, and then now we have t minus 3 equals 0, t equals 3. Okay, so it looks like we have when the velocity of the particle is equal to 0, that's happening when time is equal to 3. So now I take that time is equal to 3 and I'm going to plug it into the acceleration function. First, I need to find the acceleration function. So I'm going to take the derivative of the velocity function. That's going to be 6t minus 8. And then I am going to evaluate that for when time is equal to 3. So I have a of 3 is equal to 6 times 3 minus 8. And that is going to give me a of 3 is equal to 10 meters per second squared. Okay, that's it for now.